Hello everyone, welcome back to lecture 3 of Electronics 1. Following up from last lecture where we looked at ideal voltage amplifiers, where we modeled it around a voltage controlled voltage source, and we ended that lecture showing that the overall gain was simply equal to the gain of that voltage controlled voltage source. And we talked about some of the assumptions we made, that we assumed that the input resistance of the amplifier was infinite, the output resistance was 0, and that the source resistance was also 0. Let's follow up on that today and look at a more real-world example of a voltage amplifier. Okay, and I'm going to build this around a image I've drawn from Cedar Smith. So this is figure 1.6 from Cedar Smith. I think this is actually figure 1.6a. So here we see our real amplifier model, and you'll see a few differences. We now see that there is a input resistance on this amplifier. We'll see an output resistance, but before we go all the way to this real model, let's analyze it kind of step by step, and let's first analyze it just incorporating the input resistance. So taking the model from last day, and rather than having that input go into an infinite resistance, let's have it go into some resistance that we'll call Rin. We'll leave the output the same initially here with 0 output resistance, and the output voltage being a function of the gain times the input voltage. Okay, so here is our modified voltage controlled voltage source here again, but now we'll note that it has some input resistance that is not infinite. Okay, so I'll add on to that a load here, RL, and I'll add on a source, but this time I'm going to make my source a real source. And what I mean by a real source is that it has a source resistance. Okay, so here, connected to the input, is a real source. Okay, and what changes that source from what we looked at last day, so I'm just going to label that lowercase v subscript s, and the component that's different here, maybe I'll highlight this in a different color, is that we added this input resistance here, or sorry, source resistance. Okay, so when we take into account this source resistance that is now not 0, and this input resistance that is no longer infinite, now you should recognize that the voltage that actually gets applied at the input here, right, VI at this input, is divided down due to the voltage divider that results from RS and RI. Okay, so state there that we have a voltage divider at the input. Okay, So that results in the input voltage that appears at the input of my voltage controlled voltage source being divided some reduced version of the source voltage, unlike in the ideal case where the input voltage was exactly equal to the source voltage. So the input voltage is now equal to the input resistance divided by the source resistance plus the input resistance times Vs. Okay, simple voltage divider formula that we've seen many times before. Okay, one thing that you should note is due to this voltage divider, the input voltage here is always going to be less than the source voltage. Okay, we might say that my source voltage, might say that my source voltage has been attenuated. Okay, we looking again at the output, and if I label the output voltage here as the voltage that appears across my load, Vout, in this particular example where we've still not included an output resistance on my voltage controlled voltage source or my voltage amplifier, my output voltage is still simply equal to my gain times my input voltage. Okay, so when I combine these two equations together, so take this equation and substitute it into here, I end up with an expression for output voltage that is gain times Vs onto our input divided by Rs plus our input. Okay, doing a slight rearranging here, I can come up with a gain term. Remember, the gain is typically defined as my output voltage. My output voltage divided by my voltage from my source, or my voltage that's delivered to my load divided by my voltage that's supplied by my source. So rearranging that formula above, I see that my gain, my effective gain, is the gain of my voltage amplifier times our input plus Rs divided by Rs plus our input. Okay, so recognizing that this term here is always going to be less than 1, I'm recognizing that this is my amplifier gain, I can note that my effective gain, let's give this a name here, let's call this effective gain. My effective gain is going to be less than my amplifier gain. So due to the non-infinite input resistance, due to the fact that the source is going to have some resistance associated with it, I'm going to have an effective gain, or an overall gain, that's less than my amplifier gain. Okay, let's continue on with this idea, but now let's go and use the full amplifier, voltage amplifier model. So here's my real voltage amplifier model. Okay, so now we see I've also included this output resistance. Okay, I didn't include this in the last analysis. Okay, so this being my real voltage amp, my voltage controlled voltage source that's not ideal now. Now when I put a load on this, we see that I have to account for this output resistance that's here and the impact on the voltage that appears at the output. I'm just going to rewrite this voltage at the output here just to highlight it. Okay, so that voltage on the output is also going to be impacted by the output resistance, and we're also going to encounter a voltage divider effect at the output. So at the output now we have a voltage that's generated due to the input. That's equal to the gain times the input voltage. So whatever voltage is at my input times my gain will give me my my voltage that is generated here. Okay, but the voltage that actually appears across my load out here is that voltage times the voltage divider. Okay, so that voltage divides across RL and RO. Okay, let me redraw this. Let me maybe take this figure out of here because it doesn't show up nice on this black background. Okay, so now my true real voltage amplifier, taking into account both my output resistance and that's not zero, my input resistance that's not infinite. We have an output voltage that is impacted by that voltage divider on the output. And again here we can make the observation that due to this voltage divider term, which is always going to be less than 1, I'm going to get another further attenuation at the output. Okay, so now combining both the input attenuator, okay, so this input effect that we saw here, or well, maybe more specifically here, that attenuation that we saw here, and combining this attenuation that we saw here, so combining both the input and output attenuators. So an attenuator, just a device that reduces the gain. We now are going to get an effective gain, right? An effective gain being the gain that appears across my load, which we've called V out, and the as it relates to the voltage that's applied back here at the source. Maybe I'll add the source into this diagram as well, just for completeness. So this as compared to the voltage that's applied back at the source. We have two attenuations happening. So the gain of the amplifier is attenuated by the voltage divider at the input, and it's also attenuated by the voltage divider at the output. Okay, so we have two terms that are less than 1 here and here, multiplying together and with the amplifier gain to create an overall gain that is known as the effective gain, that is a reduction or a reduced gain from that gain of the amplifier. Okay, so we had our amplifier gain we have our input attenuation effect, and we have our output attenuation effect. Okay, so both of these effects combine to create a effective gain which is less than the amplifier gain. Let's just do a check to make sure that this expression we came up with makes sense relative to the ideal case we looked at last day. So if I do a check on this equation and say, well, last day we said ideally a voltage amplifier would have an input resistance that's infinite and an output resistance that's zero. What would be the impact of that on this equation here above? Well, my effective gain would be equal to my gain of my amplifier times a Ri, which is infinite, an input resistance, times an infinite resistance plus Rs. Okay, so I can ignore the Rs term because that becomes irrelevant compared to infinity. So that term is going to cancel out. Over here, I'm going to have a voltage divider effect on the output that's a function of the load resistance divided by the load resistance plus the output resistance. If that output resistance is 0, well, we just have RL over RL, and again that term cancels out, so my effective gain is equal to my amplifier gain. And that's exactly what we said last day was the gain of my ideal amplifier. If we go back here and look, that was the conclusion we made, that the overall gain of this ideal amplifier was equal to the gain of my my voltage amp or my voltage controlled voltage source. Okay, so that's a look at a improved model for a voltage amplifier that's more realistic and models in those loss components that we are going to see in any real amplifier.